Math 2414, volume shells. A new technique, the shell method. In the previous video, we had an example where we were going to find the volume of the solid found by revolving this lamina around the y-axis. The problem that we ran into is if we tried to do the washer method, we would have to take a cross-sectional cut perpendicular to the axis of rotation, and therefore it would be a dy integral. The problem is this equation is not easily written as a function of y. And there's also two problems. As a function of y, the equation doesn't represent a function of y because it fails, well, basically the horizontal line test. But if we were to do this as a as a washer, then the right side, the outer radius, would be this part of the graph, and the left side, the inner radius, would be this part of the graph. So we would have to take this equation, not only solve it for x, but figure out which part represents the right side and which part represents the left side. In other words, it would be a mess, maybe even impossible. But that's if we chose to take a perpendicular cut and spin it around the x-axis to make a washer. But what would happen if we didn't take a cut perpendicular to the axis of rotation, but rather a cut parallel to the axis of rotation? Now I'm going to cut what's called a representative rectangle here, because if you go back to the early days, well, the late days of Calculus 1, when you first did definite integrals, you started by cutting areas under a curve into rectangles approximating the area, found the sum of those, and then took a limit as the widths of the rectangles approached 0, and then you got the definite integral. So let's kind of take the same approach here. Let's take a little skinny rectangle here and imagine what would happen if we took this rectangle and revolved it around the y-axis. If we took that and revolved it around the y-axis, we would get what's called a cylindrical shell. It's a cylinder, but it's mostly empty. Do some shading here. There we go. So this would revolve around the y-axis and give us a shape like that. Well, if we can find the volume of that, then we can set up a Riemann sum, let the limit of the widths of these rectangles go to 0, and then we're good to go. Now the benefit to this is this rectangle's skinny side is in the x direction, meaning that this would be a delta x. So when we set up the integral, it would be a dx integral, meaning that we would want this equation as a function of x, which it is. So if we can figure out the volume of this shell, then we should be able to come up with a new technique and we'll apply it to this problem. So how are we going to do this? Well, if we want to kind of approach this generically, let's start by representing this equation as a function. It's not really changing the equation, but now we can talk generically about this from a functional perspective. And let's figure out where the coordinates of this point are relevant in that picture. The coordinates of this point would be some x comma f of x. X is how far you travel from the origin to the right. So if you can imagine the axis of rotation going right through the center of this, then x would represent the distance from the center out here. Okay? And f of x, the y-coordinate, is how tall this rectangle is. So that would be the height over here. And then the delta x would be the width of this wall, if you will. So what's the volume of that? Well, I thought about going through all the geometry that would lead to the volume, but I'm going to leave it to you to refer to the textbook that you're using. If you're in my class, it's Essential Calculus Early Transcendentals, James Stewart, 2nd edition. But the volume of the shell is 2 pi times x times f of x times delta x. This f of x clearly represents the height. It's how tall it is. This delta x represents the thickness of the shell. Well, what does the 2 pi x represent? Well, this might look a little more familiar if the x were represented with a different letter, one meaning radius. Because think about it, it looks like a radius of a circle. 2 pi r, that's the formula for the circumference of a circle. This represents circumference. Or you could say that x represents radius. So if the volume of one of those shells would be 2 pi x times f of x times delta x, then the total volume of the whole lamina would be the sum of all those shells. So this is the volume of one shell. And so the total volume would be the sum of things that look like that, 2 pi x f of x delta x. And then, well, that's the approximate volume. Because remember, when you cut something into rectangles like this, you're getting an approximate value. And to get the true volume, the true total volume, would be the limit as delta x approaches 0. Because remember, that's how Riemann sums do their thing. We make these rectangles that are skinny, call their widths delta x, and then we take the limit as that shrinks down to 0. The limit as delta x approaches 0 of the sum of 2 pi x f of x delta x, but that's just the definition of a definite integral. So that would equal the integral from a to b, whatever our limits of integration are, of 2 pi x f of x dx. And this is the formula that we're going to use for what's called the shell method. And I want to emphasize again that this f of x represents the height of that rectangle. And I know a minute ago I said that this is the circumference, but I want to focus a little bit more on just the x. Relative to the shell, the x essentially represents the radius. It's technically the average radius of the inner and outer parts of the shell. Well, that's one way you could look at it, but we'll say that this is radius, which is really the distance to the axis. So let's see if we can pull this off of this problem and we'll get our volume. All right, so we want to find the volume of this solid of revolution using the shell method. We simply have to set up the integral over the range of x values, which is 0 to 2. We found those in the previous video, of 2 pi times the distance from the axis to the rectangle, which is x, times the height of the rectangle, which is f of x, but in this case, f of x is 2x squared minus x cubed, dx. And now it's calculus 1 problem. Let's do a couple of things. Let's pull out the 2 pi. And let's distribute the x. Why? You don't integrate products. You integrate sums and differences and a few trig functions and exponential functions. But you don't integrate products. So if you can get rid of them by multiplying, great. X times 2x squared is 2x cubed. X times x cubed is x to the 4th. So we integrate 2x cubed minus x to the 4th dx. Don't forget the 2 pi. The integral of 2x cubed is going to be 1/2 x to the 4th. If that was too fast for you, pause the video and work it out. Minus the integral of x to the 4th is 1/5 x to the 5th. This is going from 0 to 2. Another convenient situation where the lower limit annihilates the antiderivative. In other words, substituting 0 here makes this equal to 0, so we can ignore it. I need to stress that the only time you can ignore something is when the lower limit makes the antiderivative 0. Don't just always assume I can ignore the 0. You can ignore it if this number makes this 0. Not the upper limit, the lower limit. So we just have to worry about the upper limit. We get 2 pi times 1/2 times 2 to the 4th power, but 2 to the 4th power is 16, minus 1/5 times 2 to the 5th power, but that's just 32. And even though I know that, let's just go ahead and do the math. So we get 2 pi, half of 16 is 8, 1/5 of 32 is 32 fifths. So there's the 2 pi, and if we get a common denominator of 5, we multiply this by 5. This would be 40 over 5 minus 32 over 5 is 8 over 5. We can treat the 2 pi like a 2 pi over 1 and multiply, and get 16 pi over 5, and that would be the volume of that lamina, that solid obtained by revolving the lamina around the y-axis. So it's a new technique called the shell method, and I want to say this now, but it'll be written clearly in the next video. The time to use the shell method is when your rectangle, your cut piece, if you will, is parallel to the axis of rotation. If you cut it perpendicular to the axis of rotation, you use the disc or washer method. And the easiest way to remember that perpendicular is disc or washer, but parallel is shell. Number one, parallel and shell kind of rhyme. Number two, the word shell literally has parallel lines in it. We'll tidy this up at the beginning of the next video and do another example.